get started. I know we have to wait for officials to be here. 7 o'clock. So any questions from yesterday that clarify before we go on? There was a question about whether the phase in the CKM can be rotated away if one of the quark masses is 0. And I hesitated. I said, no, I think the answer is no. You can rotate away when 2 quark masses are equal. And I explained why, because I mentioned 2 freedom to make rotations. And I checked, it's true. When the quark mass is 0, that's not sufficient to rotate away a phase. So I just want to clarify that. Okay, so I want to start today by discussing flavor changing neutral currents. Is this big enough for people sitting in the back? So flavor changing neutral currents, although the subject originated in trying to understand whether currents, meaning interactions mediated by vector particles, exist that change flavor while the vector particle is a neutral particle. It's now a subject that more generally refers to any type of interaction that changes flavor at a vertex where there's no charge exchange. So I'll try to explain that as we go along, but I just wanted to make it clear that this should probably be called flavor changing neutral transitions, because it's not necessarily currents that are involved. So what do we mean by that? Let's look at the standard model for a second. In the standard model at tree level, if you want to change flavor, let's look at a simple case. In fact, think of the most basic thing that you know, how we discovered the weak interactions, which is nuclear decay, although not necessarily neutrons, but neutrons are easy to think about. What's going on here, of course, is that you get a D quark that changes into a U quark, emitting a W minus, which then becomes, of course, an electron with an antineutrino. So here's a case where you have a flavor change. You go from a D quark to a U quark, but the interaction involves a charged vector boson. If we stick to tree level and want to see what a Z transition can do, so a neutral vector particle, which can be either a photon or a Z particle. You see that, we saw that yesterday, you change flavor here, but not at each vertex, right? So, in fact, if you look at this, the way I wrote this transition, flavor is not changed. The net D flavor of the left-hand side is 0, the net D flavor of the right-hand side is still 0, and each vertex, more obviously, is flavor neutral. So can we have flavor-changing neutral transitions in the standard model? And the answer is yes, if you go beyond tree level. So this is tree level at one loop. Oh, good thing here. At one loop, I can do something like this. There's lots of examples, and we'll go over a couple today. But I can do something like this, which is a very, very famous transition. I have a B quark. Here's the W minus again. And here I have an S quark. And in the loop, I have any one of the charged 2/3 quarks. And I can emit a photon anywhere I want from any one of these charged lines. So this is a B to S gamma transition. You can see that you change flavor, and there's a neutral particle in the balance. So if you thought of this as an interaction between a B quark and an S quark and this vector particle, the vector particle is neutral, but there was a flavor change. So you do get flavor change neutral transitions in the standard model, but they're suppressed. And they're suppressed because this is one loop, not tree level. So the initial suppression factor is, strongly speaking, G2 squared or 16 pi squared. One of the wonderful things of the standard model is that there's actually more suppression than that. And that's what we call the G mechanism. And I'm going to explain the G mechanism. I'm going to explain the G mechanism in 2 steps. I'm going to explain to you first kind of an old version of the G mechanism, which is outdated. I'll tell you why it's useful, in any case, to look at it, and then I'll present to you a more modern version of it. So, the G mechanism. Now, GIM, the GIM, is an acronym for the authors of the paper which first used this observation, Blasio, Iliopoulos, and Mayani. To explain it, I'm going to make the assumption, so this is what I call the old one, the old version. I'm going to assume that the quarks, M, U, C, and T, are all much lighter than the W. In fact, also the charge minus quarks are assumed to be lighter than the W, but they're not going to play a role here. In any case, this assumption is not good. You may notice that the top quark is actually not much lighter than the W, so we'll have to correct that. That's going to be the new version.
Did the old version have the top quark? Did the old version had the top quark? They only had.
So let me tell you where the old version comes from. The old version comes from the fact that the G mechanism dates back to early 70s, and in fact, before we knew about B quarks that are on the top quarks. So by the 80s, we had discovered the B quark at 5 GeV, or 4.5, and you should do the exercise of looking through the old literature to find papers predicting the top quark mass, and you find every number between 10 GeV and whatever. But most of the predictions, I'm sure if you do statistics, you'll see an accumulation at around 10 GeV, and then they decay away. Of course, until the band was put, and then it shifts, and theories predicted higher masses. So for a long time, we were working under this assumption, and that's why I'm going to present it that way. But there's some nice simplifications, which will explain to you the mechanism in a simpler way. And I'll explain to you also why it's useful in tectonic physics in this fashion. So, does that answer your question? So let's look at this process that I have here on the board. And let's imagine that I compute the amplitude. You sit down and you do this computation of a Feynman diagram, right? It's not that difficult. There's some obvious factors. So this guy, I'm not going to rewrite the diagram. Well, here it is. Just a sketch of it. There's going to be a factor of an E, the electromagnetic coupling. That I can get straight. There's going to be a G2 squared over 16 pi squared. Well, 16 pi squared because it is a loop, but G2 squared because there's 2 couplings of the W, one here, one there. Now, since I'm going to emit a real photon, and I characterize this photon by some polarization vector epsilon, this thing will have to be proportional, and so this is momentum Q polarization epsilon. It's going to have to be proportional to Q mu epsilon nu, with mu and nu anti-symmetrized in order to get a real photon. It's just like F mu nu in field space. So I also need spinors for this line. So there's a Dirac spinor for the S quark, so P prime, say, for the S quark, with some spin I'm going to do. And there's a Dirac spinor for the B quark. And there should be a 1 minus gamma 5 in there, because the 2 vertices here have 1 minus gamma 5s. And I need something with 2 indices, mu and nu, to eat up these indices there. But if I put 2 gamma matrices here, gamma mu, gamma nu, and I have 1 minus gamma 5 at each one of these vertices, so I would get, when the complex conjugate, you get a 1 plus gamma 5, that thing would vanish. So what really happens, in fact, is that in order to have 2 left-handed spinors here, you can have 3 Dirac matrices, a gamma mu, a gamma nu, and a momentum. the only two momenta around are p slash or p prime slash. You can always arrange for those to hit the spinors. When p slash acts on the u quark, gives you an MD and turns into a right-handed spinor. When p prime acts on the other spinor, it gives you a strange quark mass and turns that into a right-handed spinor. Well, this strange quark mass is tiny, so let's neglect that one. So I'm going to let the p slash act on that guy. That will give me a factor of MB. And the two remaining gamma matrices. So there's going to be this is going to be a right-handed spinor. So right like this: 1 plus gamma 5 over 2 u of p. And the two remaining gamma matrices have to be anti-symmetrized, so I get a sigma mu nu. This is all from thinking. You can, of course, do the computation, but you know you have to get this. If you're not good at doing this, you should get good at it, because otherwise it's going to take forever to do computation. And then there's an integral that you have to do that I haven't done, right? And of course, what I'm going to do is called the integral I. And there's one more factor which is important, but I included it in that I. So let me examine this I. Well, what I missed here was the fact that I'm summing over three quarks, u, c, and t, and that the vertices here are not just G2, but they have the CKM factors that we discussed yesterday. So I'm going to have to sum over u, c, and t, and there's going to be, so when we produce a charm quark, this is a CKM. So this is a V charm quark, UCOT. This is VIB, and the other one has a star, like that, from our definition of the CKM. And now there's the integral that I have to do here, and this integral that I have to do is going to be a function of the mass of the W, of the momenta going around the loop, and of the mass of the quark. Now I'm going to make an approximation. I'm going to say, well, look, let me work at, in the approximation in which that moment is very small compared to the W, and just neglect powers of that moment over MW. And in fact, by dimension analysis, I can then first take a factor of MW squared here, and then get a function which is a dimensionless function of the parameters, which I can write as the mass of the quark over MW. In fact, I'm going to write as the square. Do I do that in my notes? Yeah. Because you know that the sign of the mass of a quark cannot matter. So, and as I said, I neglected here the momentum. It will become a little bit clearer why in a second. And there might be other factors of square root of 2 and 3s and stuff like that. That's all included in F, so I don't have to worry about it. Now, here's the interesting thing. This is the fantastic thing about the G mechanism. Since I'm assuming that these masses are small compared to MW, I can take this function and expand it in a Taylor series expansion. So I can say this is f of 0 plus mi squared over MW squared, the derivative of the function at 0, and so on, right? And then the first term that I get here is the sum of VIB, VIS star, times f of 0, which I can factor out because it doesn't depend on the quark. Then the next term is still a sum of that form, VIB, VIS star, but now the quark mass stays inside the sum. I can factor out the f prime of 0, and so on. And notice the very first term vanishes because the matrix is unitary, and unitarity means that this sum is equal to the Kronecker delta of the two indices Bs, which happen to not be equal. So that term is 0. Neglect that term. And this term is suppressed by a power of the small mass of the quark over the W mass squared. Now, in the approximation that we're using, that's a large suppression. So not only we have the loop suppression, but in the standard model you get this additional suppression. There's one nice thing that I'd like to point out, which actually comes in very handy. If we use this fact, the fact that this is unitary, you can rewrite this sum over, which one did I choose? This is the sum of 3 terms that add to 0, so I can use this to write the sum of 2 terms. It would be IB, BIS star, to be the negative of the third one. Very trivial, but I can apply that to this term that remains, and now write that I is equal to the sum over I equal only U and C, and the last term I'm going to rewrite the VTB VTS in terms of the sum with a minus sign. So it's going to look like this: VIB VIS star, and I'm going to have the quark mass minus that of the top quark divided by m Dalton squared. And of course there's corrections to that. Oh no, I missed the f prime. Now, what's nice about this is that it shows you one of the things that we talked about earlier, that when two masses are equal, you can always diagonalize the mass, the CKM further, and there should be no flavor changing transition there. And you see that this actually vanishes in that case. Okay. So the bottom line is that flavor changing neutral transition is additionally suppressed. Not just the loop, there's the ratio of masses. And if you notice a little bit closely, the factor in front is also a suppression factor, because these CKMs are all off diagonal. And so you have, remember, the off diagonal CKMs have these factor suppressed values as well. Then I don't know why, but I computed in my notes what the order of these things is. You can see right away that when this is a charm quark, you get VCV, which is order epsilon squared, VCS, which is order 1. So this is order epsilon squared. When this is a U quark, you have VUV, VUS. So VUV is order epsilon cubed. VUS is order epsilon, so it's order epsilon to the 4th. So the U quark piece is order epsilon to the 4th. And the charm piece is order epsilon squared, so you can just neglect the U piece and only keep the one with the charm. So I'm going to discuss the modern version of this momentarily, but I want to make a very brief comment that if you do the same thing for leptons, if you add to the standard model a massive neutrino, because you have to account for the massive neutrino, be it a Majorana neutrino or a Dirac neutrino, you're going to have a very similar situation where where there's a matrix that mixes flavors in the charge current, just like the CKM matrix. It's called the TMNS matrix. It's completely analogous to this. And if you want to compute a transition like this, for example, with a muon going to an electron plus a photon, and you guys must have heard about MEG experiment, which is trying to do for mu3 gamma, you would have neutrinos running around the loop. And neutrinos are all very light compared to the W. So this approximation is a good approximation to make in that case. And you will see that, in fact, in the standard model, a transition like mu3 gamma is suppressed not just by the loop, but by some PMNS matrix factors, but by the neutrino mass square or the W mass square, which makes it incredibly small. Okay. So the modern version of this, well, you notice that in the modern version, I mean, I'm going to take MT to not be small. In fact, I'm going to take MT to be about 2MW, meaning it's the same order. Meaning I shouldn't do this expansion in a Taylor series because it's just not going to work. What we like to do is just, of course, keep the whole expression for this function where the top quark is running around the loop, and expand maybe for the other quarks. But you notice that not much is going to change in this expression, except this mt squared over mw squared will become the function of mt squared over mw squared. And therefore, this additional Jim suppression is encoded in the fact that you still get these factors of epsilon squared and epsilon to the 4 for the two contributions.
How do you tell anything about the form of f? Is that just matched up phenomenologically?
So f is the result of integrating this, doing the loop integral. And I'm not doing that for you because I don't want to waste our time. I'll show you some other example later on where I'll display the function. They're really, these functions that you get from this type of integrals are rational functions of this parameter. So think of this parameter. So it gets on like a polynomial divided by another polynomial, plus a log times a rational function. It's very simple.
So you pulled out the mw square when you were doing this. So
I pulled this one out. Yeah, to get the right dimensions. So if you look at the dimension of this amplitude, then you see that it has to have dimension 1 or mass. Another way to think of this is if you think of this as I shouldn't say dimension 0, if your spinors are normalized to 1. So I knew that it had to be, since I had an MD and a Q, there had to be something with dimension 2. So I pulled out an MW square, and that is implicit in what I mean by defining this function now. So you might wonder if when I did that, I don't get in trouble because f of 0 might diverge. Maybe there's a term which goes like mw squared over the quark mass, and I'm expanding about that. But you can see that this function would be perfectly reasonable. It would be perfectly reasonable to do this integral when these quarks are massless. There's no infrared divergence. So by dimensional analysis, the whole thing should go like 1 over mw squared. Anyway, so what I would say is that in the modern version, what you say is roughly, I'm going to do this very roughly in the interest of time, that this integral is dominated by the top quark with order epsilon squared times some function that you have to compute now. Well, you have to compute that area before 2. And this happens to be true because we know the function we computed explicitly is an increasing function of the argument. So by the time you get to very large values of the argument, this power of correction, this minus mc squared, is a very tiny correction. So you can neglect it. So you get this suppression, which is a 100, times the loop factor, which is another whatever, 100 or 1,000, compared to tree level. And that's oh, good. Thank you. That's the magic of the standard model. There's a little historical note I should probably add. The G mechanism was introduced in trying to understand the mass difference of K0 and K0 bar. And in the days in which we only had discovered the up quark, the down quark, and the strange quark. And we'll talk about this mass difference later on, but it involves a loop diagram, which, if you don't have a charm quark, this cancellation cannot occur. Basically, you don't have a complete unitary matrix, so you can do this trick here. So this term doesn't vanish because you don't have a charm quark. Forget about the top quark. You don't have a charm quark to solve. You only have the U quark running around. So the result would give a far larger mass difference than the actual observed mass difference. And what Jim did is they say, well, if we add an extra quark, let's call it charm. This factoring front is going to be a unitary matrix, and the leading contribution will have to automatically vanish. And then they went on and said the next term, which is a correction for this m charm squared, would get too large if this mass of the charm quark is bigger than about 1 or 2 GeV. So this was done before the charm core was discovered. And that's the historical importance of this G mechanism. It actually at once predicted the existence of charm and gave the correct mass. Okay, so let me see how we can use this in the context of putting bounds on new physics. And what I'm going to do is I'm going to model the new physics by adding to the Lagrangian a dimension 5 operator, which can produce B2S gamma. Again, I have in mind taking some new theory, which somehow has very short distance effects. You integrate those out, and it produces a change in the standard model Lagrangian in addition by an operator that looks like F mu nu, E times, and it has to be gauge invariant under the SU2 plus U1 gauge interactions. And so I want a right-handed B core, so I guess I'm going to call this B right. And then I need a sigma mu, and then the strange core has to come from a doublet because it's going to be left-handed. And then since this is a doublet, I have to add a Higgs here to make this thing invariant. And as written, this is a dimension 6 operator. I said 5 before, but that was wrong, I guess. So I'm going to put a 1 over lambda squared. Lambda is some scale characterizing the new physics, and we want to see how well can we do in characterizing this new physics scale. So to do that, I can now go to unitary gauge. And in unitary gauge, this will basically give me an expectation value, omega that of √2. I'm going to do an order of magnitude estimate. What I put down as √2 on the board is a mystery. Then there's an F mu nu. Then, of course, when you pick up the web, you pick up the neutral part of this, the part left, sigma mu nu be right. And you can read out the Feynman rule for that. Just looks like what I wrote down on this line. This combination of spinors, polarization vector, and momentum q of the photon, except that the prefactor, instead of being this subject times I, is just simply EV over lambda squared. So we can compare that to the standard model. I can take the amplitude from new physics and divide that by the amplitude predicted by the standard model, and I can impose that this be less than, say, 10%. That's because experimentally the standard model agrees with the standard model agrees with experiment to better than 20%. So I'll put a 10%, actually better than that. But anyway, so since I'm doing all order of magnitude estimate, I could have made that 1 instead of 0.1. Got kind of the same result. So what goes into that? This just says that the ratio of, well, E is common. So I can write V over lambda squared divided by, so what are the factors that we have? We have this epsilon squared, VTV, VTS star, right? We have some sort of alpha over 4 pi sine squared theta Weinberg. So this G2 squared over 16 pi squared is alpha electromagnetic over 4 pi sine squared theta Weinberg. You know this from the fluid interactions, right? And of course I have this MV over MW squared. So I know everything in that ratio except lambda. And if I say that this is less than 0.1, I can get a bound on lambda. Lambda has to be bigger, and I plug this into a calculator, and I'm really bad at that, so someone should check it. But I got that number, just by plugging those numbers. I actually kept the square root of 2. So if you get something different, it's different by the square root of the square root of 2. Okay, you should be amazed. You should be going, wow, 70 TeV is a pretty high scale. Okay? And this is why people care about flavor physics, because it throws very short distance scales that you'll never be able to probe at the LHC or any accelerator in your lifetime, let alone mine. So what about minimal flavor violation? Remember we talked about that yesterday, where I said things get aligned better. So this thing actually is not minimal flavor violating. To make it minimal flavor violating, let me change this thing and call this a D right, where D now means the whole triplet on their flavor of D right under D, S, and B. And then Q is also the triplet of doublets. The triplet of doublets, probably common. And of course, I can make this flavor minimal flavor validating by putting in the matrix lambda there. Or actually, say here's lambda dagger. I think it's lambda dagger. I think it's in my notes. Here's lambda dagger, which is actually the operator we looked at yesterday at the very end. And we know that what happens from that discussion is that we get a CKM element and a big quark mass. And if you just redo this analysis, taking away the CKM element suppression and the big quark mass suppression. So remember, this is the big quark mass in units of the graph of B. So this gets replaced by the graph. Then what happens is, if I plug in the numbers correctly, the bound becomes less bigger than 14. So this is something that you might be able to see in your lifetime. If you have new physics that that is hiding under B2S gamma because we haven't found it there, and the new physics is arranged to satisfy minimal flavor validation, then there's a chance that that new physics has a mass scale characterizing it as low as a few TeV, and you have a chance to discover it. Let me see if I can show you something. So as this goes down, what I'm going to show you is the analysis, like the one we did for B2S gamma here, although done a little bit more carefully, for the bound on the scale of new physics from different processes without assuming minimal flavor validation. And so here's a scale of new physics in TeV. So this is some B2S transitions. Actually, they're not B2S gamma. These things are other things. We'll talk about them later. But the range of bounds that you get are in the 10 to 100 TeV range. Remember, we got 70 from B2S gamma, so this is consistent with that. If you do KK bar mixing, or the CP validating part of KK bar mixing, that's light blue, the scale of new physics is bound to be at least 10 to the 3 TeV. And from CP validation alone, it actually has to be bigger than 10 to the 4 TeV. And so on. You can read the rest. I guess it's pretty obvious. But the thing to take home is that flavor physics, they're from very stringent bound on physics that doesn't align with flavor. And what I wrote here is that as an exercise, you should try to estimate how much these bounds get relaxed when you turn this into minimal flavor validating. Okay. So I'm going to turn now into a discussion of mixing. There's this mixing phenomenon that can happen in any neutral meson system. So the D0 and the D0 bar can mix into each other. The B0 and to B 0 bar, and to B sub s, and to B sub s bar. And they're all they're all characterized. Well, they're all understood in the standard model in terms of a diagram that looks like this, which can turn a meson into its anti-meson by the exchange of a couple of topos. We'll study this a little bit more. What I wanted to show you here is that the different systems have actually very different behavior. So these mesons decay. That's where you always have this probability of observing, for example, that B0 is going to 0 in time. Same thing here and same thing there. But in addition to decaying with time, the meson can oscillate into an anti-meson. And it's most obvious in this B sub s case where the oscillation is very fast. So not only is the green line decaying exponentially, but it's oscillating. And you see that as the probability of observing a B0 goes to 0, the one for observing a B0 bar grows from 0 to some maximum and so on. They alternate. And that's because we have assumed in this picture that you start with a B0, and as it oscillates, as it evolves in time, it's becoming a B0 bar. So that's why these things are kind of mutually exclusive. So it's a mixed state and an unmixed state that you're observing. Okay. So let's understand that physics. So I'm gonna actually discuss this first in the context of K-mesons. And the treatment is very similar for P-mesons and D-mesons. So there's no real loss of generality by concentrating on K-mesons, except for the fact that there's this horrible historical accident that the notation is different. The notation used by the community that does K-physics is different than the notation used by the B-physics community, and is different from the notation used by the D-meson community. So I'll introduce you to the K-ons and B-mesons, and I'll let you deal with D-mesons by yourself. If you're smart enough, you can handle it. So I was, why do we care about mixing? Well, I don't have to tell you. You just saw the previous slide. The thing that was most sensitive to new physics was the KK bar mixing column, although the other columns also involved mixing in the other systems. So you care because it's the most sensitive to new physics. You care also because it's the first place where CP validation was observed in nature. So that's kind of a good thing to know. And the other reason you care is because it's kind of a really neat phenomenon. I mean, it's a state turning into an anti-state. Go tell that to your neighbors. No matter can turn into antimatter. Ooh. So let me explain the epsilon parameter. I don't have to call it that. And this as I mentioned, is used exclusively in the context of K-on physics, and there's a corresponding thing in the B system and the D system. So in order to understand this, people talk about flavor eigenstates. Sometimes they call them weak eigenstates. We've never understood why they would use that terminology, but flavor eigenstates, whereby that you mean that the K0 is something that has the quantum numbers of an S and an anti-S quark and a D quark. And the K0 bar has the quantum numbers of an S quark and an anti-D quark. And so you can look at the K0 at the state of if you want to be a purist, you look for, in the absence of weak interactions that will make it decay, you look at the state, the lowest energy state with those quantum numbers. And if you act with CP on this thing, and I'm going to be looking at these states at rest, because I really just care about a meson oscillating into itself. I don't have to have it move. I might as well just have it at rest. So this thing, large conjugation turns this into an anti-K0, and these are pseudo-scalars. So it actually parity changes the sign. And then Cp on K0 bar does the opposite. And you can see that the sum of the difference of these two states are eigenstates of Cp as written, right? So the sum is Cp even, the difference is Cp odd, and the fact that the actual eigenstates that you see in nature are not eigenstates of Cp tells you that Cp is violated. The epsilon parameter measures precisely that. So let's see how that works by putting some equations in. I'll do a little formalism that we're going to need for other stuff. I'm going to describe the two meson system in terms of Hamiltonian, which is 2 by 2. So H with a tilde underneath is a 2 by 2 matrix. And if the states were absolutely stable, I would, and since they're addressed, the evolution would just be by their mass, right, to the IMT. Although it's a two-body system, if the evolution has them oscillating to each other, that mass matrix would not have to be diagonal. So this M here is a 2 by 2 Hermitian matrix that describes that. But in fact, the thing can decay. So I'm adding an anti-Hermitian part to the Hamiltonian by putting an I times a Hermitian matrix. So this matrix gamma describes by how much we're losing information by letting the state decay into other states which are outside the two-body system, the two-state system. Of course, we have a full Hamiltonian for everything, and we should be able to write these guys in terms of the full Hamiltonian, and the full Hamiltonian is nice and Hermitian. So this is just a way of modeling the fact that we're only looking at a two-state system. Okay. Now, I'm going to write this out explicitly. For one reason, it's not. What I wrote down doesn't look like the most general matrix that you would get, assuming that M is Hermitian and gamma is Hermitian. What's happened here is that I introduced the assumption that CPT is a good symmetry, and CPT, and you should check this, CPT forces the diagonal terms to be equal to each other. And then that's it. The other diagonal terms are just related by the fact that it's matrix M and gamma are Hermitian. If you want to give up CPT, you relax that condition, and in fact, the kind of study that we're going to perform can be generalized, so you can study violations, possible violations of CPT invariance, and there's papers that deal with these and compare with experiments. Okay, so I promise that these matrices, in fact, can be computed in terms of some more fundamental physics, and I'll show you briefly. So in fact, you can actually find this in quantum mechanics books. So this is not something very deep. This matrix Ij, there could be some diagonal term. Well, there is a diagonal term by CPT, but then I'll explain what I'm writing in a second. It's like another perturbation theory, kind of. I mean, it is. You just have to read carefully. Okay, looks like that. There's a 2 pi, there's a delta of the same thing. And here I and j just stand for I and j is 1 is K0 2 is K0 bar. Okay? So it's just a shorthand, so we can write it in terms of free indices. So basically, this is second order perturbation theory. H is the Hamiltonian, the basic Hamiltonian in your theory. We assume that strong and electromagnetic interactions have been done exactly. So these states, I and J, are the exact states in the theory, absent weak interactions. And then we do perturbation theory in the weak interactions. And H is the Hamiltonian density in the weak interaction Hamiltonian. The states are normalized. For this to make sense, if you look at the dimensions, the states are normalized in the non-relativistic fashion, just like Jorken and Drell. Instead of twice the energy times the delta function, it's energy over mass times the delta function. If you don't know what I'm talking about, check what normalization of state is in a relativistic theory. The principal part here is just picking the propagation part. The kind of more obvious thing to say is that the decay width is associated with transitions where the state n can go on shell. So you have an initial energy n, which is the mass of the K0 or K0 bar state, and it can decay into a state with energy En. But that energy En has to be equal to the original mass n. Whereas here, the principal part ensures that, in fact, that doesn't happen, and that's why you have a propagator that doesn't really blow up. So you're summing over states that don't have the same energy of the initial state. Is there anything else I need to say about that? I think if there's any questions asked, I may have missed some explanations. Okay, so with that we'll be able to relate this system we're going to use to describe what happens in oscillations to the actual underlying theory. That's why we wanted these equations, and we'll use them eventually. So now let's actually kind of find the eigenvalues and eigenvectors of this 2x2 system, and the eigenvalues we're going to call minus I over 2 gamma short, which is just m minus I over 2 gamma plus 1/2 plus minus I over 2 delta gamma, and this is a whole bunch of definitions. You compute the eigenvalues from here, which is you're clever enough to deal with a 2x2 matrix, I guess, and then you can relate those eigenvalues to this definition, which is all kind of hard to read. So there's two states, these state that I'm calling L and S. Maybe I should make it more explicit. KL or KS minus I over 2 gamma KL and KS. The upper and lower correspond to the upper and lower signs here. And these are just a whole bunch of definitions of what I mean by delta M and delta gamma, and what we mean by the actual eigenvalues. But they're all computed in terms of this matrix. And the eigenvectors also will introduce some definitions. So there's a KL and a KS. And they are given in terms of a parameter called epsilon, which is what we're trying to introduce. So here's what we've done. I mean, I'm doing two things. One is I want to point out that if epsilon were 0, this would be just the sum and the difference of K0 and K0 bar. This would be CP eigenstates. So epsilon, as I said, is what measures the failure of CP to be a good symmetry. And so it does that, and also this is defining how epsilon appears. So again, if you compute the eigenvectors of this matrix, you will actually be able to relate epsilon to these definitions. And these definitions, of course, can then be given in terms of the more fundamental underlying theory of these other definitions. It's a long rigmarole, but that's the only way to handle this complicated calculation. Now, let's do a little bit of phenomenology. Kaons can decay to 2 pions, can decay to 3 pions, can decay to 4 pions. No, not really. 4 pions are too heavy for kaons to decay into. So it can go to 2 pions, they can go to semi-leptonically to pi nu, for example, and then they can do other weird stuff. So let's look at the decay into pions. So let me point out to you that if you take 2 pions, so pi, in a spin 0 state, so 0 angular momentum, because we want to consider only the case when they come from a spinless kaon, then Cp on an angular momentum 0 2 pion state will just give you pi. The pi can be a pi plus pi minus, which turns by charge conjugation into pi plus pi minus, or a pi 0, which turns into pi 0, pi 0. Parity gets minus sign for each pion, you get minus 1 squared, that's plus 1. Very simple. Now let's do Cp of 3 pions. Also, angular momentum 0. Here's what angular momentum actually matters, because if you take a wave function which is not angular momentum, well, actually also here, if the wave function doesn't have angular momentum 2, the wave function doesn't have angular momentum 0, the wave function can actually change sign under parity. You exchange the momentum of the 2. For angular momentum 1, you get an extra sign. So angular momentum 0 is very simple, which is what I said before. So you get 3 pions, they go into themselves by charge, and parity changes the sign 3 times, so this is minus pi. So, if Cp were a good symmetry, epsilon would be 0, and the sum the sum of these two states would be, no, I haven't right. Sorry. I said it wrong in rows. I said it wrong in words, but I have it right. If you take the sum of these things, as they both change sign, the sum is odd under parity. The difference is even under parity. Sorry. So this is correct. So if epsilon is 0, the upper one, k long, would be an even state. Sorry, an odd state. So Cp k long is minus k long, which tells you that it could only decay into 3 pions. Whereas k short, which is even, the difference of k0 and k0 bar, could only decay into 2 pions. Right? So what happens? I can probably stick it in here. Experimentally, here's the case. Here's the branching fraction. So we're going to have k short to pi, k long to pi, and k long to pi. So k short to pi has branching fraction 100%. Actually, there's an error bar, plus minus 0.24%. It actually can decay into something else. It's just that most of the time it goes into 2 pions. K long to 3 pions happens there 40% of the time with some error bars. I wrote them down in my note, but I'm not going to call them. It was 39 point something, it was minus point something. Very special. And K long to 2 pions happens 0.3%. But 0.3% is not 0, and this one I should actually write down with error bars, because I want to show you it's not 0. This is 0.297 plus minus 0.023%. So the fact that K long goes into 2 pions tells you that CP is violated. And this is how it was discovered. And what I like to do now is figure out how this number tells me something about this parameter epsilon. And if I can do that, maybe I can then try to compute epsilon from the weak interactions that we've been discussing and compare and see whether the standard model actually can account for that number. Yeah. Questions?
To make sure, this CP violation is not the one from CKM matrix.
To be sure, it is exactly the one from CKM matrix in the standard model.
But is there a difference between CP violation from mixing or just from the decays of the?
Well, this is, okay, very good question. This is what we call CP violation in mixing.
Right.
And it's obviously where the word comes from. The name comes from the fact that it shows that the states that are mixing with each other fail to be in a CP eigenstate by epsilon. Now, what could be happening, of course, is that this is a perfectly good CP eigenstate, and it's the decay process which breaks CP. What I haven't told you is that in the standard model, the violation of, and actually also by direct observation, the violation of CP in the decay process is much smaller than the one in mixing. So you have to take it for granted for now, but this CP violation here is all coming from the mixing and not from the decay process. Okay. Incidentally, because of this, the S and L stand for short and long. And the fact that K long cannot really decay into 2 pions, but only to 3 pions, and the fact that the 3 pions have a mass that adds up to basically the mass of the K long, it's a little bit less, means that the phase space available for this decay is very suppressed, which means that the decay time for the K long is much longer than for the K short, which can decay into 2 pions. And so it actually turns out that the K long has 100 times longer lifetime than the K short. And it has this interplay between CP, the nearly good symmetry, and phase space, which is a peculiar thing in the chaos system. It doesn't happen for B mesons and D mesons. Okay. So now let's try to find epsilon. And this whole discussion is in the standard model. You know how to extend the discussion beyond the standard model by, say, adding these operators that could modify the discussion. And it's really true that any extension of the standard model can be characterized that way. Any viable extension of the standard model. Okay. So now you actually do the computation of relating the eigenvalues to the matrix, and it's very, it's a one-line computation. So I'll spare you the computation. This is equal to twice m12 minus I over 2 gamma 12 over m delta m minus I over 2 delta gamma. It's also equal to 1/2 between the complex conjugates here. It's useful to write it both ways because this actually tells you how to write delta m and delta gamma in terms of m12 and gamma 12. So you can solve for that. And notice that, oh, so one thing I forgot to say, and I think, still here, right? This matrix. You can check that CP, so CP basically exchanges these guys, right? Because exchanges K0 with K0R. So CP is a good symmetry if M12 is equal to M12 star and gamma 12 is equal to gamma 12 star. So CP is violated only if there's an imaginary part. And we know the violation is small, so I'm going to assume that the imaginary part of M12 is much smaller than the real part, and the same thing for gamma 1, 2. Just because I know already experimentally that epsilon is a tiny number, so why not use that? And we'll see that it actually works out like we're in the standard model. So, okay. So, so now epsilon is a small number. These numbers are also small. I can expand this in epsilon. I can show what epsilon is. It takes a microsecond. So this is then I times imaginary part of M12 minus I over 2, imaginary part of gamma 1, 2, divided by delta M minus I over 2 delta gamma. And I'll use a little bit more phenomenological information to do this fast. In fact, it turns out, just from observation, this is kind of a weird coincidence, but delta M is about minus delta gamma over 2. Just take it for granted. You can look it up in the particle data book. That's what it is. And the reason for that is that if I use that, then this number is 1 plus I times delta M. So I can write this as a phase e to the minus I pi over 4. Then I is e to the I pi over 2. So I can rewrite this using another piece of information that will actually justify later. If I get it. No, I'm not going to get to this, but this can be justified. The imaginary part of gamma 1, 2. I'll mention this later. I'll justify this. So just use this. And then you get a very simple formula if you do all of this. You can write this as e to the I pi over 4 times the imaginary part of M12 over delta M. But delta M is square root of 2. Is 2. The root 2 comes from 1 plus I here. So, and the delta M is 2. Parts from 1, 2.
Sorry.
Yeah.
Where does the imaginary part of M12 comes from? I thought that M was our real.
So M is a Hermitian matrix.
But it's not real.
And it's not real.
But
it's real if CP is a good symmetry.
But addition, the M part of the matrix, just the propagation part, and the gamma, the imaginary part.
So M of course is real. And gamma is real because it's a Hermitian matrix, and along the diagonal, that means the terms are real. But M12 only needs to be, the Hermiticity of course just tells you that this element here is the complex conjugate of that.
I think the
and
way
CP invariance tells you that they're real.
I think the way we write M plus I over 2 gamma is you can just write any anti-Hermitian matrix in terms of 2 Hermitian matrices.
Right, so the point here, this was not a totally random, this is of course an arbitrary matrix now because of Hermitian matrix plus anti-Hermitian matrix. But it's not, I didn't try to write this the motivation for writing this is physics, right? I can write M explicitly this way, and I can gamma explicitly this way, and I have an understanding of what they mean physically. M has to do with propagation, gamma has to do with decay.
Yeah.
Wow, okay. Fantastic. So, so what can I do with this? I'll try to, this is actually fairly general. I mean, I made some assumptions on what's small and what's not, but I haven't used the standard model at all. So if you have some other theory of nature, you can still apply this here. I'll come to the standard model in a minute and try to predict in the standard model, but we can, I'll take a little detour to show you how epsilon is measured experimentally most cleanly. And that's by measuring, because this is still kind of model independent before I go into the standard model. So let's define an asymmetry where I let the k long decay into either pi minus e plus or pi plus e minus. You can think of this as the k long oscillating into a k0, which can decay, because that's a favorized eigenstate, decaying one way, or into a K0 bar decaying into the charge conjugate way. And if the amount of K0 and K0 bar is different in the K long, this will measure that. Well, if you can do the calculation, the width is some mass times the amplitude square, mass being phase space. And the amplitude square is going to be, if you write K long in terms of K0 and K0 bar, there's going to be a 1 plus epsilon times the K0 part going to pi minus C plus, and then a 1 minus epsilon part going to pi minus C plus. And since only one of them can go, you can check right away. This is the same as 1 plus epsilon squared. All of the factors in front are common, so they cancel out. And since epsilon is small, this is twice the real part of epsilon. And the measurement for this, experimentally, this is 0.33%, which gives for this, for the real part of epsilon, 1.65 times 10 to the minus 3. So epsilon is small. And that's consistent with what we saw at the level of branching fractions, but this is really a direct consequence of oscillation. And here we assume, we don't have to assume that there's no CP violation in the decay, because K0 can decay by the weak interaction at tree level directly into pi minus C plus, but not into pi plus C minus. Okay? So there's no assumption there. Okay. So let me sketch for you in the remaining 7 minutes how you compute epsilon in the standard model, and this will relate to everything we've talked about so far, including Jim and all of that good stuff. And then tomorrow I'll mention briefly what happened to the P0 system. And so epsilon in the standard model. Well, look, we have this formula here. What I need to do is I want to compute the imaginary part of M12. In fact, I won't even bother to try to compute the real part of M12 because that's delta M. I can get that experimentally. There's another reason why I don't want to compute the real part of M12, and I'll explain that momentarily. Okay, so an M12, you will remember, is 1, which is K0, and Hamiltonian K0 bar, plus the sum, principal part, of K0, Hamiltonian, and Hamiltonian K0 bar, divided by, I'm not being very careful with my signs, so I think this is, take it with a grain of salt. I think that's right, because, yeah, it's right. So how do I compute this? Well, we know what the Hamiltonian is in the weak interactions. At lowest order, the Hamiltonian. I want the principal part. Right. So this this is not necessarily real. The numerator is not necessarily real. So you pick up the real part from the numerator, from the denominator, but the numerator has the imaginary part. So for the Hamiltonian, I could take the weak vector times J mu, for example, and then if I want to have something that changes a K0 into K0 bar, then you draw a diagram. We already saw it once. I have an S. So here's my K0 turning into a K0 bar. It has an anti-S and a D. Time is going to left, from left to right. This would involve then 4 of those interactions, and I would have to expand this formula to 4th order, which looks like a total mess. But there's a better way to do this, because we know that all of these interactions are happening at fairly low energies compared to the W. And so we know that, you know, from Fermi theory, kind of works, where I can say, for example, let me take the first entry here. Let me put a U quark on this side. I can say that this interaction is well represented by 4 Fermi interactions, and I can write it like this, the US, where there's no W anymore. What happened, of course, is that the propagator for the W, this propagator, which is a minus I, G mu minus Q mu over M squared, when the momentum going through that is very small compared to the moment to the mass of the W, can be completely neglected. So I can neglect that and I can neglect that, and this whole thing is just I G mu over M squared. And if you connect that, the 2 currents with that, you get a contact interaction with coefficient 1 over M squared. So I'm going to imagine that I'm doing that, and then the Hamiltonian appears, for this transition, I have the Hamiltonian once, twice. So I can actually use this formula to compute with 2 insertions of the Hamiltonian there. Okay. Now, this can get a little complicated because the intermediate states here are U, C, and T. And when the intermediate state is a U quark on both lines, the states that I'm summing over can involve things like 2 pions, 3 pions, 4 pions. Really 4 pions, they don't have to be on shell anymore. And these denominators can get fairly large, and this computation can get very messy and very difficult. However, when these quarks are U quarks, the CKMs connecting T to U and S to U in the standard parametrization that we introduced yesterday are all real. And the only place that you can pick up a phase for this imaginary part of M12 is from the phases in those vertices. So this is what I said. I don't want to deal with the computation of real parts of M12 because I will have to deal with those intermediate states. But the imaginary part of M12 only requires that I include the heavy states. And the nice thing about the heavy states is that they're so far off shell here that I can kind of do the same thing again. This is holding an effective theory, and I'll talk about that tomorrow. I can take this whole thing when these guys are C and T and replace these by just one single interaction where you have the T going to S and the anti-S going to an anti-D. Okay? And these, if you don't understand what I mean by these, I just mean an interaction of this form, S bar gamma mu D, which is a left-handed force, twice S bar gamma mu D. That's what this means. And there's some coefficient in front that I'm ignoring, but we'll get to it in a minute. And then, okay. And I should just mention very briefly terminology. This thing that I'm trying to avoid computing, where all of those states actually can contribute, that's called a long distance contribution in this context. And contributions like this one, where all of the states that would go there are very virtual, and I can replace these by a contact interaction are called short distance contribution. Okay, so here the advantage of looking at imaginary part of M12 only is that it's all short distance and I can actually compute something. So let's imagine we do that. Let's imagine that I take the imaginary part of that diagram. The imaginary part of this diagram, which have the K0 bar, this thing, I know I only need C and T here, and here you have D to S, S to D. Okay. Well, I'm going to do the same thing we did with D to S gamma. I'm just going to say, let's pull out some factors that are pretty obvious. It's usually written as G Fermi squared times something, but you can see that it has to have a dimension of 1 over mass. There's a loop, so I put a 1 over 4 pi squared. And now there's the sum of CKMs. Let me call them VQ, V star, VQS. It appears twice, one for the top line, one for the bottom line. So sum over Q, sum over Q prime. Then there's a function coming from doing that integral. And now the function depends on the quark on each one of the two lines, Q and Q prime, over mw squared, just like before. So it's very similar to what we did before, but now it has two masses that we have to deal with. And finally, there's this operator, S bar, let me write like this, S bar D, which is what I brought down there, but I'm saving time. And remember, this was in that formula where I'm computing matrix element between K0 and K0 bar. And the way to understand that is, once I make that whole interaction a local interaction, the whole Hamiltonian contributes to delta is equal to this. Oh, here it is, sorry. So the whole Hamiltonian can be just stuck directly into that term. So that's what I've done. Now, to complete the calculation, we need some idea what this function is. But, you compute it. I can show it to you. It's not very, it doesn't tell you much. We have an idea of what this is. We can let the lattice people deal with it. I'm going to write it as it's usually done. It's the decay constant of the kaon, times the mass of the kaon quantity squared, times the parameter, which is a Hodge factor to get the right answer, times 2/3 by definition. And the 2/3 by definition is done so that this parameter here would be 1 if you computed this naively by inserting the vacuum in all possible places as intermediate state. And use the fact that 0 is the A0 is Fk. So that defines Fk, and that tells you that if you insert the vacuum state here in the middle, you will get an Fk squared times P mu times P mu, but T squared is Fk squared, so you see where that comes from.
Sorry, how are the other states reversed? The ones that are not the vacuum?
Yeah, so you can. So the other possibility is you can make a Cleave rearrangement and move these, exchange these to these. So then you get the same quantum numbers, but you have a color TA there and a color TA there, and you pick up from that product the singlet part that can contribute to a vacuum insertion. I didn't say that right. It's not a TA. It's this color contracted with that and this color contracted with that, and then you can break that into a singlet of the singlet piece as a 1/3 contribution. That's where the number comes from. And why this is more than 1? That's because this is defined to the gamma mu gamma 5, and these are left-handed fields. There's a quarter for the 2 1/2. So if you didn't have the left-handed, which is 1 minus gamma half, it would be an 8/3. Did that make sense? I went too fast.
No, well, the question was why are you just considering the as an intermediate state vacuum? And how are the other ones?
There's no good reason. Oh, perfect question. There's no good reason. This really just parameterizes this matrix element in some units that seem reasonable, and it's chosen so that this B would be 1 in that approximation. But the actual thing, the actual computation has to be done non-perturbatively. People on the lattice do, and what they find is that B is around 0.3. And finally, the other comment I want to make is, as I run out of time, in this calculation, since, you know, the sum here of 3 terms, if we had the sum of 3, we have to add up to 0. The first term is completely real. That's why we left it out, which means that the imaginary part of the second term cancels the imaginary part of the third term, which is again like a G-type mechanism. So there's only one term that characterizes the whole thing. So let me just write down the answer, and you put all that stuff together. So you put it all together, and you write epsilon. Using that expression, so there's an I pi over 4. This is my last equation. Some coefficient. I use for that the Wolfenstein parametrizations. I'm going to write a squared lambda to the 5th eta. Eta is the imaginary part that I'm picking up. Right? Then there is a squared lambda pi times rho. Is the function of mt with mt. Actually, it's mt squared over w squared, but I'm running out of energy. And there's a term, the minus lambda f c times c, and another term which is a cross term with a plus lambda f of c and mt. And then this coefficient c, which has its factors of g, Fermi, fk squared, and k squared, all that good stuff, and w squared e over 6 root 2 pi squared delta m k. You can compute some number like 2 times 10 to the 4, which is pretty big, but then this number here is pretty small because you have pointed to the to a very large power. Then these functions of MC, again, are very suppressed because you get factors of m charm square over w square. But the one with the top part, which is not suppressed, has a lambda to the 15th one. So it turns out you can actually plug in numbers. All of these numbers are comparable in magnitude. And when you multiply them by the 3 factor, each one of them is itself order 10 to the minus 3. And the remarkable thing is that experimentally, epsilon is 10 to the minus 3. So the standard model is 10 to the minus 3 as the sum of 3 contributions. Each one of them is about 10 to the minus 3. And the fact that it gives precisely the right number is a very kind of interesting test of the quality of the standard model. So I'm going to stop there. And what I want to do tomorrow is I want to talk there's a few things that you should have noticed here that I did that are kind of not very kosher. For example, you might be wondering what happened to the contribution with a U fork and a charm fork, because I put charm on top and charm on top. I dismissed the up and up. How about the mixed one? So I cheated. I have to explain why that's okay. Another thing where I cheated was I said, well, I can make this into a complete kind of local operator. And all of the QCD interactions, all of the strong interactions will go into computing this matrix element of this operator. And you might be wondering what the heck happens when you have a gluon going from inside the loop to outside the loop, which is not really accounted for there. And I'm going to explain how effective field theory takes care of all of that. So that's the plan for tomorrow. And after I explain that, I'll go back and do a little bit of the B0s. And that will be
note that we have a coffee break, and then it says physics discussion.